Welcome back to thermochemistry and thermodynamics. In part 2 of this unit, we're going to be talking about enthalpy, more commonly known as delta H. And one of the ways we're going to calculate enthalpy is by using bond energies. So we'll get into bond energies and what that is and what that means. Let's get started. So first of all, enthalpy pretty much refers to a transfer of energy through heat. Specifically, enthalpy, which we know as delta H, is the total heat content of a system. I like to think of H being heat. This is equal to internal energy of a system plus the product of pressure and volume. You might remember that we looked at these on video 1, the internal energy and the product of pressure and volume, which was pretty much the work. You're not going to have to use that as a formula to calculate enthalpy. We're going to find other formulas to calculate enthalpy, but that's just where it's coming from. Now, when enthalpy increases, delta H is a positive number because heat and energy are transferred into the system. This is known as an endothermic reaction. Endothermic, taken in. So it's a positive value because heat is added, so adding heat is positive. But if enthalpy were to decrease, delta H would be a negative number because heat and energy are transferred out of the system. This is known as an exothermic reaction. Exo, given off. So if it's losing heat and energy, it's negative from whatever it was before. So in endothermic versus exothermic reactions, an endothermic reaction, over the course of the reaction, kinetic energy decreases because potential energy increases. Since in a closed-off system, there's a conservation of energy, one energy has to transfer to another. So there's greater potential energy in the bonds of the product molecules than in the reactant molecules. So in an isolated system, kinetic energy is transferred to potential energy. In a system that's open to surroundings, kinetic energy is transferred into the system, and the surroundings thus lose heat, so we're going to feel the reaction getting colder. All of this describes endothermic. There's a greater potential energy in the bonds of the products, so it has to take in heat and energy to store in those bonds, in the bonds of products, and it's taking in the kinetic energy to do that. An exothermic reaction, on the other hand, is the exact opposite. Over the course of the reaction, kinetic energy increases because potential energy decreases. There's greater potential energy in the bonds of the reactant molecules than there are in the product molecules. So in an isolated system, potential energy is transferred to kinetic. In a system that's open to the surroundings, kinetic energy is transferred out of the system, and the surroundings thus gain heat, and we feel it getting hotter. So when it's exothermic, the reactants contain more energy, potential energy, and so when they're transferred to products, they lose that potential energy in the form of kinetic energy or heat. So we're feeling exothermic reactions getting hot because the bonds are losing some of that energy as heat. So looking at this reaction, or these two reactions on our next examples, we're going to figure out what delta H actually is. So delta H simply is the heat in the reaction, but what I'm looking for specifically here was that 170 kilojoules of heat gained or lost, added or subtracted. So delta H is going to be equal to, notice that the 170 is a reactant, so the nitrogen and oxygen have to take in 170. Take in means add 170 kilojoules. For the next reaction, notice the 2860 is a product. So carbon dioxide is produced, water is produced, heat is produced. So heat is leaving the system. So in this case, delta H is negative 2860. So exothermic always has delta H on the right. Endothermic always has delta H on the left. I think technically left should probably say reactants. Instead of saying right, we should say products. So now delta H is an extensive property. Extensive property means it does depend on the amount of matter present. So if you were going to double the reaction, say double the moles of mercury, then you'll need double the heat. Or half the moles, then you'll need half the heat. So our next examples, we're going to rewrite each equation using a 1 in front of the underlying compound, and then we're going to correct the heat of reaction according to the new equation. So see here that this is 2HGO. So if we make this 1HGO, then we're cutting the mercury oxide in half. So then, to keep all the ratios the same, we would also need to cut the 180 kilojoules in half. We'd need to cut the 2Hg in half. And we need to cut the O2 in half. This is the only time that fractional coefficients are okay. So the delta H here is, instead of positive 180, it's going to be positive 90 kilojoules. So for the next reaction, to put a 1 in front of the underlying compound, I'm actually going to have to double it. 1/2 times 2 is 1, so there's 1 nitrogen. 3/2 times 2 is 3, so there's 3 hydrogens. 1 times 2 is 2, so there's 2 ammonias. And we're doubling everything, so we're also going to double heat. 46 times 2 is 92. So delta H is negative 92 kilojoules. This is an exothermic reaction. Okay, enthalpy or delta H can also be used in stoichiometry. We can treat delta H as another one of the reactants or products. So for example, in this reaction, where delta H is negative 1643, you could just take this out completely, and instead, since it's negative 1643, add it to the product side, plus 1643 kilojoules. Now there's a reason why I took off that negative. Negative shows that it's a net loss, but within a reaction, we never use negative signs, and say you lost 20 bucks. Your bank account is negative 20 from whatever it was before, but you don't go tell your friend, hey, I just lost negative $20, because then you actually gained $20. So this plus 1643 over here is saying that you lost 1643 kilojoules. You wouldn't want to say you lost negative 1643 kilojoules. Within a reaction, the number's always positive, even though if you pull it out, on the product side it'll be negative, and the reactant side it will be positive. So let's do some stoichiometry with this. 150 grams of iron. So I'm going to start with 150 grams of iron. And I know from the balanced reaction that 4 moles of iron will give off 1643 kilojoules. That's 4 moles of iron. So we're actually going to convert that grams to moles using the periodic table. Moles always gets 1. Grams always gets the periodic table. For iron, it's 55.8. That'll tell me moles of iron, but one more step. For every mole of iron, or every 4 moles of iron, 1643 kilojoules are released. So that's 150 times 1643 over 55.8 over 4. Type that in your calculator, you end up with 1104 kilojoules. This is not a negative number. How much energy is given off will always be a positive answer. But if you were to look at delta H here, that would be a negative. Let's do another one. Say you had 255 kilojoules of heat. How many grams of iron would that be? Well, 255 kilojoules of heat is what we're looking at. But we know from the balanced equation that 1643 kilojoules will produce, or is produced by, 4 moles of iron. That's moles of iron, not grams of iron, so one more step. From moles of iron to grams of iron, based on the periodic table, 55.8 grams is the mass of 1 mole. And then, according to my calculator, 34.6 grams of iron is my answer. Okay, those previous problems had you calculating delta H, but also really given delta H. The next set of things we're going to look at, actually at the end of this video and the coming video, is how to calculate delta H, like where the numbers come from themselves. Earlier we said essentially it's internal energy plus work, but then where do those numbers come from? So we're going to look at 4 distinct methods of determining delta H, bond energies here in this video, Hess's law and enthalpies of formation, these guys are both going to be in part 3, and then calorimetry, that's going to be in part 4. So we're going to look at several different ways to determine delta H in several different videos and bond energies for right now. Bond energies are the amount of energy required to break a bond. Break a bond. Energy is released during the formation of a bond because potential energy decreases as the atoms move closer together. That same amount of energy must be added in order to break the bond because potential energy increases as atoms move further apart. So when calculating delta H using bond energies, we're going to look at energy required and released when breaking and forming specific bonds in a chemical reaction. Products are given a negative value because product bonds are being formed, not broken. So for these problems, you're going to have to look on the reference sheet that you've been given. On the very back of the reference sheet, there's a bond energies chart. And that bond energies chart is where we're going to get these numbers from. So right now, pause the video, find that reference chart. Okay, hopefully we got there. So we're going to determine delta H using bond energies. And so for that, we need to know what bonds are being broken and what bonds are being formed. It's a good thing we've already talked about how to actually draw bonds or Lewis structures. Now we're not going to be specific here with our Lewis structures. The idea is just in H2, there's 2 H's bonded together. In Cl2, there's 2 Cl's bonded together. In HCl, there's an H bonded to a Cl. But since there's 2 of them, there's actually 2 H's bonded to a Cl. So look on your bond energies chart. Find hydrogen on the left and follow it over to hydrogen on the top. And you'll see that a hydrogen-hydrogen bond requires 435 kilojoules to break per mole of HH. Here we've got 1 mole of HH, so that's 435. If you find Cl down the left and then follow over to Cl on the top, you'll notice that chlorine, a chlorine-chlorine bond, requires 243 kilojoules per mole to break, and here we have 1 mole. If you find HCl, find H on the left-hand side, follow it over to Cl on the top, and you'll notice that HCl requires 431 kilojoules to break. But here's the thing, we're not breaking HCl, we're forming HCl because it's a product. So it's the opposite number. And there's 2 of them, because this is kilojoules per mole, and we have 2 moles, so we're going to take that whole number and multiply it by 2. Once you've figured out your numbers, then just add them all together and equal them up. 2 times negative 431 is negative 862 plus 243 plus 435. Get out your handy-dandy calculator. Hopefully you end up with negative 184 kilojoules. One more example. Determine delta H again using bond energies. You need to be able to draw the pictures of the bond because we're trying to figure out which bonds are breaking. So CH4, that's a C with 4 H's around it. O2 is O double bond O, but there's 2 of those O double bond O's, so we're actually going to draw that twice so we don't forget. CO2 as O double bond C double bond O. We've just done this, but I'm just trying to remind you. And then water should be H, O, H, H, O, H, twice because there's 2 of them. So let's look up the bonds on the chart. For the CH bond, that's going to be, find on the left, followed over on the top, 414 kilojoules per mole. But how many moles do we have here in CH4? I see 1, 2, 3, 4 CH bonds, which means there's 4 moles of CH that need to be broken. 4 times 414. For O2, there's 2 moles of O double bond O that need to be broken. Notice that there's only one O double bond on the left as you follow it over to find O, and that's going to be 498. Then we've got CO2, that's a C double bond O and another C double bond O, 2 C double bond O's. So let's find that C double bond O on the list. It looks like it's 803. And then for water, we've got 1, 2, 3, 4 individual OH bonds. So finding an OH bond, that's 464. Now what you have to keep in mind about bond energies is that they're the energy required to break bonds. So products are not being broken. Products are being formed. Products need to have their sign flipped. But other than that, it becomes a giant addition problem. 4 times 414 is 1656. 2 times 498 is 996. 2 times negative 803 is negative 1606. And 4 times negative 464 is negative 1856. You should always check my math to make sure I multiplied those correctly and make sure that you and I are getting matching numbers. When we add that together, I got negative 810 kilojoules. That's how much energy required to break a bond, or required to form this entire reaction. Now, bond energies are not exactly as accurate, say, as some other methods, because an HO bond requires 464 kilojoules per mole to break. But notice that that chart doesn't take into account whether it's water gas or water liquid or water solid. It seems like those 3 different things would require different amounts of energy to break. So bond energy is not the most accurate thing ever, but it still gives us a good idea. Alright, that's all we have for today. Join me next time for a couple of different ways we can calculate delta H. See you then.